So one of the limitations on this U is equal to mgh equation is this g. This little g only works close to the surface of the Earth. Close to the surface of the Earth, we've got that the weight force is equal to mg. Whereas when we move further and further away from the Earth, we need to use the equation F is equal to g m1 m2 over r squared, where this is the mass of the Earth and this is the mass of whatever object we're considering. So as you move further and further away from the Earth, this little g actually changes and gets smaller and smaller. And so this gravitational potential energy equation only holds for objects on the surface of the Earth.
Hydroelectric power plants have several advantages. One of these advantages is that they're considered relatively environmentally friendly. The main adverse environmental effect comes from when the dam is built. At the moment, the Three Gorges Dam is being built in China. This is the biggest dam that has ever been built. And as a result of the building of this dam, a lot of land has been flooded, which has meant that a lot of small townships have had to be moved. However, when you're producing hydroelectricity, you do not release any greenhouse gases, such as in the burning of coal, etc. So actually generating the electricity is doesn't have inverse consequences for the environment. A big advantage of hydroelectric power stations is that they can actually provide electricity very much on demand. If there's a lot of electricity in the system, so there's actually spare electricity, then rather than generating electricity, these hydro power plants can be used to store that energy. So they can actually pump water from a lower height to a higher height, and so that increases the gravitational potential energy stored in the water and is actually a way of storing that energy. If there's then a high demand for the electricity, the water can move down from the high height to the low height, and as it does so, its gravitational potential energy is released, and if it goes to a hydropower plant, converted into electrical energy. So let's consider exactly how a hydroelectric power plant works. Here's a diagram showing you a hydroelectric power plant. You can see that we're not actually taking the water from the very top of the dam, we're actually taking it from near the bottom, which makes a lot of sense because if the level in the dam drops, you don't want to be left high and dry without any water flowing through your power plant. So this doesn't actually affect the amount of energy that the power plant can get. That's because at the bottom of the water here, the water is at a high pressure due to the weight of all the water above it. So the work that the water can do is given by the force times the distance, and force, which it can supply, is given by the pressure times the area. So as the pressure increases due to the increasing depth of the water, the force that it can apply to the turbines increases, and so the amount of work it can do increases. So it actually turns out the same as removing water from the very top of the dam. So we've said that the amount of power generated is equal to the energy over the time. So hydroelectric power plants have an efficiency. So efficiencies are always between 0 and 1, and they basically tell you how good a power plant is at converting the supplied energy into the output energy, which goes into electricity. So hydroelectric power plants are very efficient. They have efficiency constants close to 1. So the amount of power is equal to the energy lost from the gravitational potential energy over the time times the efficiency. So the gravitational potential energy change, remember, is given by mgh, where h is the change in height of the water. So in the video 2 in this topic, we saw that the volume flow rate was given by the cross-sectional area times the velocity of water through that point, which is also equal to the volume of the water that flows through a point over the time. And we said that density is equal to mass over volume, So we can say that volume is equal to the mass over the density. So the volume flow rate is also equal to the mass over the density times the time. So let's combine all those equations now. So the power supplied by the power plant is given by mgh times the efficiency, which will give the letter K, over the time. And now we can replace the mt in that equation with rho AV. So the power supplied by a power plant is given by rho, the density of water flowing through it, times A, the cross-sectional area, times V, the velocity, the flow rate, so AV together are the volume rate of flow, times G, times H, times K. So let's do an example now of using that equation.
So the question is, calculate how much power is generated by a hydroelectric power plant through which 22 meters cubed of water flows each second. The water is 120 meters above the bottom of the dam and the plant is 80% efficient. So we're going to need to use our formula that the power generated is equal to the density times the volume flow rate, AV, times G, times the height of the dam, times K, the efficiency. So we know the density of water is 1,000 kilograms per meter cubed. Now this is the volume flow rate and we're told that 22 meters of cubed of water flows through it each second. So this AV is just 22. Now G, that's just the acceleration due to gravity, so 9.8. H is the height of the water above the dam, which is 120 meters. And then K is between 0 and 1. 80% means that it's 80 over 100 or 0.8. So now all we need to do is put that into the calculator. So when we do that, we get 697,600 watts. So we can write this as 20.7 megawatts, where mega is 10 to the 6th. So this is how much energy would be generated in a relatively small hydropower plant. Some hydropower plants can generate a lot more electricity than this.
So in this video, we've seen that dams can be used to store water and actually raise the height of the water. We can then release energy from dams in a hydropower plant by letting the water flow through and do work on a turbine. As the water loses that gravitational potential energy, that energy goes into work on the turbine and that can be used to produce electricity.